section 6.1, and we are going to give a question on this. Okay, it's from that section that's going to be on functions. So so let's go back to see the last thing that I did was the famous PowerPoints. Okay, so if a set would be given, we are able to list all the subsets. Okay, and we know that if the set would have n elements, then we have 2 to the n subsets. So we're going to denote that one by P of A, and we call it power sets. So the members of the power sets are sets. Okay, that's going to be the one. Okay, now I'm going to introduce a function on these power sets. Okay, so I give you an example. So this example, in your field, you are going to have functions as defined. You know, in calculus, you define the function on an interval. You define a function on a collection of, a set of numbers, but you don't introduce a function on a collection of sets in calculus. So this is this example is all about. So this example is a function. Okay, this example is going to be a function defined. It's going to be defined on a power set. We use this type of function in probability. And there is a great part of mathematics that we call it measure theory. The measure theory is a very difficult field. And this is where we study the function on the sets only. Okay, so this example is going to be of this format. See, suppose A is going to be a set of 3 members, A, B, C. Then a function. You see, I'm going to define a function. This function is going to function f. Okay, so the domain of this function is going to be power sets of A. So the domain is going to be power sets P of A. Okay, and the range of this function is going to be just numbers. Okay, it's going to be non-negative numbers. Non-negative numbers means positive integer. Okay, these positive integers, or may 0, and we may use 0 too. So this notation means natural numbers 1, 2, 3, 4, 5, 6, and also 0. Okay, so a function f okay, so what we are going to do is, so suppose going to be the function, this function is defined. Okay, is defined for each. You see, the member of your domain is going to be a set. So it's going to be for each set x, not a number in x. Set x, which is going to be in P of A, in the power sets of A, okay, is defined by, for each set, by the following, if you like, by the following statement or the formula. So the statement is going to be f of x. Okay, f of x, so x is a set. F of x is going to be the number of, you see, it's going to be the number of, and the number of elements, the number of the elements in x. Okay, the number of the elements in x. So x is going to be a set. So if this set would have 2 elements, suppose if you take the x to be a set of A and B, so f of that x would be 2, because the number of the elements on that set is going to be just 2 elements. Okay, so basically this means you get the x as an input, you see the x as an input, and you drop it into your function machine. So your function machine, f of x, would give us a number. Okay, so this is going to be the number of the, okay, number of elements in x. Okay, this is a situation we're going to have. So what we would like you to do is we would like you to find the range of this function. Find the range. We want to see how you operate with this function. Find the range of the function range of the function f. You see, that's question. The range is going to be the output, you know that. So you have to try all the inputs of this function and give us the output. You put the outputs together, that collection of the outputs would be the range of the function. Okay, any question? So to get the range of the function, you have to identify all your members of the domain. You see, because you have to drop the members of the domain into the function to get the result. So we have to find the power set of A. You know that we get A, B, C, 3 elements. So your power sets would include 8 elements. Okay, so for the solution, we say that the A is A, B, C. Okay, so it has 3 elements. Has 3 elements. And so this P of A. Okay, P of A has what? Has 2 cubed, which is equal to the 8 elements. 8 elements. Okay, this is a situation we're going to have. Now list all the members that we're going to have. So the power sets of A. We talk about it, you have to list all the subsets. Okay, you start with the trivial one, which is going to be the empty set. Okay, that's empty set. Then we are going to have whole sets, which is going to be what? The sets A. Then we consider, singleton. A set containing 1 element can be A, can be B, C. These are the set with a single element. Then the set with the 2 elements is going to be A, comma B, A, comma C. Remember, no order, no repetition. And the B, comma C. You see, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. These are all the possible members of the domain. Any question? So this is it. These are all your input. So you have to find the value of the function on all these inputs. And the function, you know how your function operates. Your function would, you give a set to the function, the output would be the number of the elements in the set. Okay, are you ready? So let's see what's going to be f of empty set. You see f of empty set, you just check to see how many members do you have in an empty set. You don't have anything. So this is going to be f of the empty set would be 0. Okay, then you want to find what is going to be f of A, or whole sets. Your whole sets containing 3 elements, 1, 2, 3, so it's going to be 3. And then you continue. You see the singleton, f of a sets A is just 1, and so the same thing for the f of just B, or the f of just C. These are all 1. Then for the containing 2 elements, okay, f of A, comma B, it's 2. Okay, f of A, comma C is 2. And the f of B, comma C, yes, that's what. B, comma C is also equal to the 2. So these are all the possible values in the range of your function. Okay, so the range is going to be the collection of these output. So the range of the function f is going to be what? The numbers that you have. You are going to have the 0, 1, 2, and 3. So this is going to be the range of your function. Any question? So these are a collection of functions. There are a couple of them in your book, and I post those numbers for you from that section that is covering the function. So you just have a look, and I put them into the text review. So when we talk about it, you are going to be familiar with this type of sets. Okay, any question? So that's going to be a function on the sets. As I told you, the other one is probability function. And you say f of, we call it P in that case. P of A, we write 20%. means the probability of getting A is 20%, or P of B is going to be 50%. The probability that we get the B is going to be 50%. That's called probability function. And these functions are called set functions. Set function because you define it with a set. Okay, so that was a brief, just a quick pause, if you like, to get to know the application of the power sets and be familiar with this type of notations. Now let's get back to the sets again. We are going to consider a couple of operations, binary operations. Remember, with the proposition, we introduced a binary operation like what? Like or, and then we did have the so-called complement operations. And from there, we introduced number of the identities for you. It's the same thing. So it's same thing with the sets. We are going to introduce, instead of the or, we are going to introduce the union notation. Instead of the and, we are going to introduce the intersection notations or operations. And for the negation, we are going to introduce the complement of the sets. Okay, and then there are some properties, some identities, exactly like the one that we did. In fact, you can define the sets first, then go back to those type of ideas. Okay, so what is going to be a couple of sets operation or set operations that we are going to introduce. There are quite a lot, but the one that we are interested in are going to be the following: union of the sets. Okay, the first one, union of sets. If you have two sets and if you put all the members together, the result is going to be the union of the sets. Okay, so if A and B are going to be given sets, okay, going given sets, and then the union, okay, the union of A and B, the notation are going to be denoted by, okay, denoted by A union B, A union B, and is defined, basically is defined to be the collection of all members. Defined to be the collection, okay, defined to be the collection of all elements. Okay, the collection of all elements in A or in B. See, this is going to be the definition of the union B, and this is it. A union B is going to be the collection of all X, with this condition that the X belongs to A or X belongs to B. That's it. So we put all the members together. If the member is going to be, if you get a common member, you just repeat it once. That would be the union. Okay, any question? Now intersection. If you consider the common elements, the elements that belongs to both sets, the result's going to be intersection. So what is going to be okay, intersection of sets. Intersection of sets. And that's it, the intersection of the intersection of the sets A and B is going to be denoted by, intersection is denoted by this one, A intersect B. See, that's it. And is defined by, and is defined by that is going to be definition is going to be the members that's going to be in both of them. So it's going to be A intersect B is going to be equal to the X such that this X belongs to A and belongs to B. Okay, it must be in both sets to be in the intersection. Okay, so that's the intersection. Any question? Next, and the last one that we're going to consider is complement. And so this would be similar to the AND connection that we did for the proposition, and the other one would be the OR. So we're going to introduce something for the negation. So this is going to be the complement. Okay, what is going to be the complement? The complement of a set. Okay. So it's going to be the complement of the set. The complement of the set is, again, remember we introduced a universal sets. All the sets are coming from a source. That source is called the universal set. So the complement of the set is whatever it is outside of the set. Okay, the element is going to be not in the set A. Is going to be called the complement of the sets. So the complement, okay, the complement of a set A is going to be denoted, okay, is denoted by A complement, AC we are going to use, okay, and is going to be defined by, that's it, the complement of the set, anything outside the set. You see A complement is equal to all the x's that are not in A. If you see, that's it. Anything outside. So this means A complement is equal to, is going to be all the members X belongs to the universal set such that X is not equal to the A. So this is your, suppose this is going to be your universal set, okay? So this is going to be your universal set, and this is going to be your set A, if you like. This is your set A. So anything outside these sets, you see anything outside these sets is going to be your A complement. So the members of the A complement is like the negation of the A that you did have. Okay, any question? In some book, I don't know, I don't remember your book, I think I checked it before. Some book that use this notation, which is very bad. A prime over here, okay. They use this one, it's like it's the same as the A complement if you see it somewhere, but mathematically it's a very bad notation because A prime over here, and my field is mathematical analysis. So we call this one a limit point set, a point set of limit points. So it's quite something different, nothing to do with each other. So you better use the A complement over here, even if you see that notation in your book. Okay, so the complement is better. Any question? Now, whatever we did with the negation for the proposition can be done with the sets. In fact, it starts with the set to have the other one. So these are the one that we used before. I'm going to write on the next page. Any question? So this observation would be again part of the questions that you're going to have. I give you usually 1 or 2 questions from these ideas on the final, and of course your next sets. So these observations are important and you can use it anytime you like. You see, note that It can be proved easily. Okay, it can be proved that you can use it anytime you like. This is it. The first one is like a De Morgan law that we did for the negation. Remember, this is A union B complement. It's like the negation of the okay, P or Q. Remember, the negation of P or Q would be negation of the P and the negation of the Q. It's the same thing for the set. It's going to be A complement intersect with the B complement. That's the first version of the De Morgan law. And if you do it the other way around, if you have the A union B and you want to find the complement of this one, so that would be A complement, a union with the B complement. You see, sorry, it's going to be intersection. It is intersect. It's going to be A complement intersect with the B complement. Okay. So that's going to be the case. The other one that we did have was the fact that, remember, we want to know what's going to be the complement of the empty set. Any suggestion? What's complement of the empty set?
The universal.
Full set.
That's it, the universal.
For number 2,
Yes.
is this supposed to be the same thing as number 1?
Oh, I made a mess on this one. Yes. No. This must be, but I did. I wanted to correct it. Sorry about that. I wanted to correct it, but I changed it into the, this must be, I write it in again. Okay. I just want to talk about it. I write it here. Okay, if you have a, you know that the one that we did, what do you call it, duality condition for the binary operation. This means if you change this operation from the union to the intersection, so this is going to be equal to the A complement, but you have to switch this one, union of the BC. Thank you. Okay, like the one that we did before. So the complement of the union is intersection of the unions, and the complement of the intersection is going to be, you know, union of the complement. So that would be number 2. Okay, we need one more. You can use this freely. Okay, especially this 3 and the 4 one. What's the complement of the universal set?
Empty.
Empty set. Very good. Empty set. Okay, because universal set is whatever we have. So if you empty that one, would be at empty set. Okay, so this is going to be the case. Again, we proved quite a lot of these identities for the negation. We can have it over here too. Okay, I just write a couple of them for you, but we are not going to use it. And if we use it, we may ask you to identify it for us. Okay, so just a remark that whatever you did before, you can collect them all here. Remark. Let's write some of them, but we are not going to use it quite a lot. But if anytime we use it, we know we just refer to the something similar that we did have in the past. Say that, you know, if A, B, and C are going to be our given sets, okay, then just remind you, you know, for example, commutative property, remember, A union B is equal to the B union C. And by duality means if you change these, it's going to be B union A. Okay, we just switch. And for the intersection, it's going to be the same thing. A intersect B is equal to the B intersect C. You know, similar one that we did before. And you can, you can list all the others. For example, associative property, it's going to be the same thing. A union B, union C, and you can go with the intersection that give you the same thing, that you are going to have A intersect B intersect C. Okay, so there's going to be the usual one. The interesting one is this next one. We are going to give you something to verify for us. Verify means I give you the identity and a specific example, then you verify, not prove. You cannot prove anything with example. But the third one is interesting, and we are going to have it in a minute. And that's the distributive law. Distributive means like A times B plus C. In multiplication would be AB plus AC, something similar. So if you have A intersect with B, a union C, you see this one? If you want to distribute it, it's going to be A intersect with B. Okay, then union with what? Union with A intersect C. It's like multiplication. It's like multiplication, A times B plus C is AB plus AC. But the surprise one is going to be, it's a duality. Duality means if you change this notation, if you switch these two binary operations, okay, then it's not going to be like the ordinary one that we like it. So that would be A union B intersect with C. You see? When you change it, it's like A plus BC. And then this would be what? This would be A union B intersect with, okay, A union C. So this second property is going to be different from the ordinary operation that we apply. This is the one that we call it distributive property, property D. Okay, this is going to be distributive property. Okay, the sets that we use, the mathematical design or model. The model that we use in computer science, you have this binary operation, those 0, 1, 0, 1, 0, 1 that you usually use. Okay, the difficulty is this property. Some of the operation model that we use would follow this property, and some of them won't. So the one that satisfies this property, the one that you use in computer science, we call it the Boolean algebra. And this is one of the popular one, Boolean algebra. Sometimes we teach this one in discrete mathematics. And sometimes you have it in a couple of your CS courses that they talk about it. Boolean algebra is going to be algebra 0, 1. Operation that we use is like union and intersection. And then the difficulty is distributive property that you have. So if you impose that distributive property, that design is going to be something familiar. So that's why you have to know the name of these and the purpose of the distributive properties. I'm going to apply it. So we may give you something, you will see it in your practice one. We may give you sets A, B, C, and we want to verify it. Verify means you are going to find the left-hand side by using the given examples, and the right, and you verify that they are the same. Okay, if it's going to be on the test, this is going to be the purpose that we're going to have. Okay, and we can have quite a lot of these identities. We are not going to use it, otherwise I can list it for you. And the one that we are going to use are going to be given to you at the next example. Okay, any question? So let's see how we're going to question you on this one so far. This question is very easy. Even on the final, some people, they miss it. So just, just get to know it, and you should be right, straightforward with this type of examples. Okay, so a couple of these sets would be given to you. Suppose the set A is equal to, okay, the set A is equal to the 1, 2, 3, 4. Okay, this is set A, and you have a set B. A set B is 3, 4, 5, 6, and then you are going to be given a universal set. Anytime they want to talk about the complement, they have to give you universal sets. So the universal set for this argument is this one. It's the 1, 2, 3, 4, up to the 9. Okay, 5, 6, 7, 8, and 9. Okay, then they ask you to find the following. So you are going to be asked to find the following sets. The following, okay, the following sets. Okay, so the following sets are going to be the following. Number one, I want to find A union B. Okay, number two, we wanted to find the A intersect B. Okay, A intersect B. And number three, we wanted to find what is going to be A union B. A union B intersects A. Okay, number four, that's 1, 2, 3. Number four would like to find what is A intersects, what's the complement of A intersect B. Number five, we ask you what is going to be A complement, okay, A complement union with the B complement. And eventually we ask you what is the power sets of A intersect B, and number C, what is U complement. So this is a kind of question. It's a kind of way we are going to ask you this type of questions. This identity, we're not going to ask you to prove it, nothing. We give you all the information that you need, and you basically have to, okay, have to find it for us to get these numbers done. Okay, so let's do it one by one according to our definition. We can do it, and we just keep going. Are you ready? There you are. Solution one by one. The first one, A union B. Remember, A union B means all the members of the A and the B. You start with all the members of the A, and then you add the members of the B. If anything is repeated, you are not going to repeat it. You see the members of the A are 1, 2, 3, 4. Then with the B, if anything new, you add it. You see you have the 3 already, 4 already. So you have the new one is going to be 5 and 6. 5 and 6. That's it. That's A union B. So it covers all the members of the A and all members of the B. And it covers once. You're not going to repeat anything. Any question? So it's A union all together. Intersection. Intersection means the common elements. You see the common one. Just check to see if you get a common element in these sets. You see, what's the common elements?
3 and 4.
3 and 4. 3 and 4. And remember, you have to use set notation. You cannot say it's equal to 3, 4. Doesn't make sense. You must have the set notation here. Okay, question? Now, let's see what's going to be number 3. You see number 3, A union B intersects with A. This is A union B. That's A union B. You want to find the intersection of A union B with the A. What's the number?
It's a set containing 1, 2, 3, 4.
Yes, this is going to be, it's equal to the A. Yes, it's going to be 1, 2, 3, 4, which is simply A. And that's a theorem, you can prove it. Because the, you see intersection A union B and the A. A union B is the bigger sets, if you like. And the A is a subset. So that give you A. But if you give you on the test, this is the way you answer it. You just compare. Any question? Everybody got it, this one? A union B, you already got A union B. You want to find the intersection with a common element between this one and set A. It's going to be all the members of the A. So that's number 3. We can do number 4 over here too. Then we go to the next page. Number 4. Number 4, you want to find the A intersect B complement. So you already got the A intersect B. You see A intersect B is going to be what? Is equal to 3, 4. So for the complement, you know that you are going to go to the universal sets and you drop 3 and the 4. This is your universal set. This is your universal set, okay? So what you're going to do is you're going to drop the 3 and the 4, the leftover. Anything that is not in A intersect B. So you're going to have what? 1, 2, 3, and the 4, you can have it. So you get a 5, 6, 7, 8, and 9. So that's going to be a complement of the intersect. Any question? Now, number 5, I'll go to the next page, explain it. A complement, B complement. You have to find the A complement. You drop 1, 2, 3, 4 from this. B complement, you drop 3, 4, 5, 6, and you get the leftover, okay? So let's go and get A complement, B complement. That's a number 5. Just rewrite it. I want to A complement union with the B complement. So we get the A complement first. Drop the A's from the universal set. If you drop the A is 1, 2, 3, 1, 2, 3, 4, universal set is 1, 2, 3 up to the 9. So 1, 2, 3, 4 out. So A complement would be what? Would be 5, 5, 6, 7, 8, and 9. So that's A complement. Okay, we get a B complement. B is 3, 4, 5. You have to drop 3, 4, 5 from the universal set. That's going to be the result. It's going to be 1, 2, 7, 8, and 9. Okay, the complement anything, everything outside of the B. Outside means in the, okay, in the other universal sets. Question? Now if you put them together, A complement, B complement is going to be what? Now it's going to be 1, 2. Okay, you can, there's no, don't need any order. If there's going to be anything repeated, you are not going to repeat it. So I write down in this order, I get a 5 and the 6. Then I get the 7, 8, 7, 8, and 9. Okay, I got everything. 1, 2, 5, 6, yes, 5, 6, 7, 7, 8. And if you compare the what you got over there, you see, note that you should have a complement of the A union B or A intersect B. Yes, this is the one that we find. A intersect B is A complement B complement. You see, this is what we did here. 1, 2, 5, 6, 8, 9. That's the De Morgan law. Okay, and that's exactly equal to what? Is equal to the A complement union B complement. So if they ask you to verify this equation on the test or on the quiz, this is the way you do it. That's just a verification. It's not a proof. It's just a verification that A intersect B complement is A complement and the B complement. Okay, any question? So not difficult, but you got to be patient not to make any mistakes and put these together nicely. That was number 5. Number 6, power sets of the A and the B. Number 6, you want to find the power sets of the A. Okay, A intersect B. So you have the intersection. Okay, what was the intersection set? So A intersect B. Okay, A intersect B was 3 and 4. You want to find the power sets, you want to find all the subsets or the possible subset. As you can see, this has 2 elements. Just remind yourself, you don't have to write it down. Has 2 elements. And so the power sets of A intersect B will have or has 2 squared, 4 elements. You remind yourself so that you are not going to miss anything. Okay, so what's going to be the 4 elements that we have? So the power sets of the A intersect B. Remember, you start with the empty set first, and the whole sets, then singleton 2 by 2, etc. Singleton is just single 3 and the single 4. You see nothing else, because with the 2 elements, it's just the full sets that you have, and 1, 2, 3, 4 elements, and then you find out that you did it right. Any question? So this is the way you operate. And the last one, of course, is easy. We already talked about it. The complement of the universal set is just the empty set. And then we're done. Any question? So this is the way we are going to check these type of the properties that we're going to have, or set operations. Just to remember it, there are a couple of things that we're going to do in chapter 8, and then we need these type of ideas to get these numbers. Now, the next one is the one that we did before, but since we need it, and of course we know we are going to mix it with these new operations. So we remind you first, and then we continue. And that's a Cartesian product. Remember the product of the sets that we did before? So we're going to revisit it. So this is another operation of the sets that we're going to be interested in. So Cartesian, okay, Cartesian products, or product of sets, cross product, some people they call it. Okay, remember this Cartesian product of 2 sets is the collection of their order pairs. It's the one that we did define, and we used it to define a relation and a function. We're going to use it when we get chapter 8 again to define relations again, and we consider some property of the relation for that final part of the course. Okay, so let's see how we are going to use it here. We have 2 nice problems in your book, so we can check it. So let's remind you the Cartesian product again. So if 2 sets are given, the collection of order pairs. So if the sets A and B, okay, if the sets A and B are given, then what? The Cartesian product. Cartesian, you know that is from René Descartes. Cartesian product. The Cartesian product A cross B. A cross B is going to be defined by this one. Define set of order pairs. A cross B is going to be what? Is going to be the collection of all order pairs. A, B, such that A belongs to A and B belongs to B. So that's the definition of Cartesian product as we did before. Okay, just remind you again that if A has, if it's if A has 2 elements, B have 3, so they altogether they have 2 times 3, 6 elements. Just remind you this one, we did it before. So if A has let's say m elements, and B has n elements, okay, n elements, then A cross B, okay, A cross B has m times n elements. That's why we call it product rule. Okay, that's one. So what's going to be your job now? You know the Cartesian product from the past, A cross B, and we have these new operations, union, intersections, and sometimes, or you can connect them together. You can connect them together. There are 2 problems in your book, in your assignments, related to this type of problems. So that's why I'm going to give you one of those examples so that you know what's going on with this type of functions. Okay, so let's get this example. First, I remind you what was this Cartesian product, and then I bring that problem. Okay, so example 1 is that if simply we have 2 sets, I just want to make sure that you use correct notation. If A is 4 and a 5 and the B is, okay, B is a 2, 3, and 4. Okay, then you are going to have the following. If you want to find the A cross B, remember 2 element, 3 element, 2 times 3, 6 elements. And we just started with, this is going to be order based. There are 2 notation. You see, this is a set notation. Inside, you use order paired notation. Order paired notation is going to be parentheses. I've seen some people, they make a mistake. They use bracket for all of them. You be confused here, okay? And you can't do it. So members are going to be what? It's going to be 4, 2, 4, 3, 4, 4. That's going to be 4, 2, 4, 3, and 4, 4. Then we come back, we pick the 5, 5, 2, 5, 2, 5, 3, 5, 3, and 5, 4. 5, 4. 1, 2, 3, 4, 5, 6. So that's how we write the okay, Cartesian product to get these numbers. Okay, any question? Now, are you ready for that problem? This is it. You have 2 in your book. So I give you one of them, and we check the other one before your next quiz test. We want to know what's going to be the relationship. You know, if we're going to be math major, you have one chapter full, you know, about this Cartesian product, various relationship that you can have. But you're another math major. So we just wanted to know, in case you see it, how you operate and what's going to be your understanding of sets or the points or the order pairs at the same time. It's the idea. Okay, so this is going to be the example. One version in your book and one version that we are going to do now. I'll tell you what will be the other version. You see, suppose A is equal to the set A is equal to the A comma B. That's, I think, exactly the same set that you use in that Excel book problem. So the A is A and the B is 1 and the 2, and the C is 2 and 3. This is 3 sets. Now, I just want to remind you, if I give you this type of question, you know what you are going to do. I want you to verify, and the proof are 2 different things. Verify the following identity, the following. identity by finding the quantity of each side, or the quantities, the quantity of each side of the equation, of each side. You see, this is identity. A cross B union C. It's like A times B plus C. You see, we have A times numbers. If you have A times B plus C, it would be AB plus BC. It's the same, it's a similar thing. So it's going to be A cross B union with A cross C. It can be proof. Verify means we just want to verify it for this example. Okay. So what I'm going to do, you have to find both sides and show it is going to be the same thing. Okay, so I'm going to call this one. You can do the same thing if it's going to be on the test. Left-hand side. And I'm going to call this one right-hand side. So work on both sides to get these numbers done. Okay. So I'm going to go with this part first, left-hand side first. So I find the left-hand side for you. For the left-hand side, I need a B union C. Okay. So let's find out what's going to be B union C. This is B and the C. So note that the things that I'm going to use for this one, I need the A. A is what? A is A comma B. Okay, and I need B union C. B union C means a union of this P and the C, the members. What do you have? You have 1, 2, 1, 2, 3. Remember, when it's something is repeated, you just repeat it once. So it's going to be 1, 2, 3. Any question? I just put these together because I want to introduce this one. You see, this would have 2 elements. And this is 3 element, 2 times 3, 6. So that the left-hand side should have 6 elements. Get the order pairs of these 6 elements. So what is A cross B union C? The first members from the A set and the second member from the other ones. You see A1, A2, A and 3. Then you come back B and 1, B and 2, B and 3. That's how you list the members, okay? So it's going to be equal to, they are order pairs, remember. It's A comma, okay, A comma 1, that's one order pair. Then it's going to be A comma 2. Okay, then we get A comma 3. We are done with the A's. Then we go with the B. It's going to be B comma 1, B comma 2, if you like, and the B comma 3. That's going to be the members of the A cross B union C. 1, 2, 3, 4, 5, 6. Any question? So that's the left-hand side. The right-hand side. You have to form A cross B and the A cross B and the A cross C and show that when put them into the union, you are going to get 6 elements here. Okay, so let's do the other way around. So how about the right-hand side? So what we have? We need A cross B. So find A cross B first. A cross B. So this is my A. A is A comma B. And this is my B, which is 1, 2. Okay, so I want A cross B. A cross B. I got 2 elements, and 2 elements, 2 times 2 would be 4. So I need to create 4 elements. Okay, 4 order pairs. So it's going to be a collection of order pairs. There you are, A1, A2, A, okay, A and 1, A comma 2. Then with the B, B comma 1 and the B comma 2. You see, this is A cross B. Any question? So for the next part, you need A and C. So this is my A and this is my C. So again, I need 4 elements for the A cross C. A cross C is equal to the A and 2, A comma 2, A comma 3, then B comma 2, B comma 3. That's it. That's A cross C. Okay, any question? Now the union of these two. You put all the members together. If something is repeated, you just repeat it once. You see, you have A11, 2, B1, B2 over here. A2 is repeated, so you don't have to add it. So you have to add the A3. B and 2 is repeated, you have to add only B and 3. Okay, so there you are. So A cross B. A cross B union with A cross C is going to be equal to all the members in the first one, which is A comma 1, A comma 2, B comma 1, B comma 2. Now for the new one, if there is anything new to add, A2 is already there, A3 is not, so it's going to be A comma 3. B2 is there, and the B comma 3. B comma 3. If you compare them together, they are exactly the same thing. Okay, so the left hand side is equal to the right hand side. Okay, which means A cross B union C is A cross B union with A cross C. So that's the verification that we talk about it. Any question? By those duality argument that I talk about, dual of these expression, dual means you just change union and intersection. So similarly, do it for yourself. Similarly, A cross B intersect with C is going to be A cross B. You already got everything we need really. Intersect with A cross C. That's the other version. I don't remember. One of them is in your book. The other one is not. Maybe the first one, second one. So make sure that you are able to do, just check the second one for yourself. So that's the most popular idea of these sets of relation that we have. We just put them together. This is the way we question you, or we wanted to know it in case, in future, you may have a situation that, you may have to use it, or you may see it. So you already got some idea of this type of operation. Okay, any question? So we are almost done. There is one more definition that we're going to use in future. So I give you that definition too. That's easy, but it's going to be used in chapter 8 of our next target. Let's give you that one too. And you have 2 problems on that. This is something clear, if you like. And that's something we call it partition of a sets. So partition of a sets means, you see, just think about the building. So in the building, we have classrooms. So if you go to the second floor, you see number of the classrooms at the college. So these classrooms partition the second floor. So when we say partition of sets, we have a collection of sets, if you like, with the condition that these classroom or sets, they have no 2 by 2 intersections. There's no overlap between the first class and the second class. There's no intersection. And if you put them all together, means if you consider union of all the sets, the result's going to be the floor. Okay, so it's partition of sets. And we have two nice theorems in chapter 8 related to the partition of sets. That's why we make a record and we define it here. So when we get to that famous theorem in chapter 8, we know what we are talking about, okay? So this is the last topic of this section 6.1 that we put together. What is a partition? Okay, that's it. Okay, let's say partitions of sets. What's the partitions of sets? Here you are, we have a set and we want to partition it, break it into parts. So suppose a set A. Okay, suppose a set A is given. Okay, a set A is given and A1, A2, up to the, let's say AN. It's going to be just a couple of sets, but at least quite a lot. Okay, suppose the set A is given and A1, A2, A2, AN are non-empty subsets of A. Subsets of A. So this A1, A2 up to the AN are the classrooms, and the A is the second floor, if you like. So are non-empty subsets of A such that two conditions satisfy. The first condition is they have no 2 by 2 intersections. So this means if you pick one of them, it's going to be, they call it AI, one of the classroom, intersected with a distinct one, and the other one, they have no intersection. So the intersection is going to be empty set. Of course, when I is not equal to the J. Okay, so this means A1 and A2, A1 and A3, A1 and A4, the intersection is empty. Then you get A2, and now A2, A3, etc. Say I not equal to the J because if you pick, for example, A1 and A1, the intersection would be A1. That's why we use this notation. Okay, so A is not equal to the J, of course, for all of them, or 1, 2, 3, up to there. So basically means no 2 by 2 intersection. This is the one. And the second one is, if you put all of them together, you must get the sets, you must get the floor. So it's going to be A1 union with A2, union with AN. All of them are going to be the set A. So they partition the set A, okay? If this is going to be the case, so suppose the subset A is given and A1, A2 are non-empty sets such that this property is true, then these sets, we write them as a P, then P equal to a collection of the A1, A2 up to the AN is going to be called, a partition. Okay, a partition of A. That's it. So we break the A into, into a smaller sets, if you like. A smaller sets, if they have this condition, we call it a partition of the partition of sets. Okay, so for the time being, just knowing it, identifying it, but we have a very nice theorem. There is a relationship between a relation defined on a given set and this partitioning of sets, and that would be quite interesting one, and we are going to discuss it in chapter 8. Okay, so this is the only example that we have. We have a couple of them in assignment of 6.1. A set and a collection of subsets are given to, and they ask you whether you are going to have a partition or not. Okay, so there you are. Suppose Suppose the set A is going to be covering this number 1, 2, 3, 4. That's set A. If this is going to be 1, then look at this one, a partition on these sets. The sets are singleton 1, 2, 1, 2, and 3, and 4. You see, the member of the sets are non-empty. They don't have any 2 by 2 intersection. You see, if you find the intersection of any of these two sets, the result is going to be empty set. If you put them all together, you get 1, 2, 3, 4, the union of all of them. So this is a partition. Is a partition. Is going to be a partition of A. Okay, any question? That, look at this one. If I give you another one, Q equal to the sets 1, 2, and the set 2, 3, 4. What's wrong with this one to be a partition of A?
They both contain 2, both of the
That's it.
subsets.
Yeah, that's it. They have intersection. They have intersection. See, the rooms must be disjoint, we say. The rooms must be disjoints. There's somebody in both of them. It's not possible. Okay, this is not. Is not a partition. Not a partition. Okay, a partition of A. And the reason is going to be, note that the reason is this one. The set 1 and 2 intersection with 2, 3, and 4. They intersect at one point. So this intersection is not empty. So that's why we cannot use this as a partition. In that example that you have in your book, they give you a list, okay? They give you a list of the partitions, the collection of sets. There are collection of sets, and they ask you whether or no they are going to be forming a partition or not. So that give you the results of we are going to have. Okay, any question? So we are almost done. We're done with whatever we need to do. So what I'm going to do is, since we talk about these products, I give you one more function, definition of a function. This function is defined on the Cartesian product of sets. Okay, so the domain is Cartesian product of sets. And this function is very popular in your field. That's the one just in your computer science. It's going to be used in coding theory. So I introduce this function too. So you must know this function. We may ask you, give you one example. Okay, so this again problem in your book. Just explain it. It's not bad so that you see this set theory. So get to know this function. Okay, so the other function that I gave you was a power set function. This is the other one. If you have done any, you will see it in code theory or a couple of other places in computer science. So we finish. I like to finish it with this one. I can ignore it, but it's good to know it. Okay, so what's this function? It's going to be a function that's defined. Okay, so a function defined. A function defined on a Cartesian product. Cartesian, okay, product of sets. You see, I want you to know it because some people, as soon as they see the function, they say, oh, this is a horrible function. Okay, but they are not. It's just when you look at it, you enjoyed it. Okay, so what is this function? This function is called Hamming function, is the name of the guy in your field. So that's it. I don't know him. Okay, but I didn't get time to check this one. But it's this function is interesting. So the Hamming, they call it the Hamming distance function. So if you say Hamming distance function on the quiz, you must know it. We are not going to give it the definition. Okay, it's going to be used in your coding theory. Coding theory. This is where you may see, you may see this is the EORY, you know that coding theory. Okay, so the Hamming distance function is the one that I'm going to use in coding theory. So how I'm going to define it? Suppose you must get to know the definition, otherwise the work is easy. Suppose Sn, S sub n is the set of all strings or sequence strings of zeros and one. You know that this is the numbers that we use for the codes of length n. Okay, so if we talk about S2, we mean only 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0. We talk about S3, you should have the length must be 3, etc. Okay, so Sn is set of all strings of 0, 1s of the length n. Now define the Hamming function. Hamming function will be defined H from the Cartesian product of Sn cross Sn. This is what? Set of order pairs. Is set of order pairs, you get two members, A and the B. Both of them are the codes of 0, 1, 0, 1, 0, 1. Okay, into what? Into Z positive. Z positive means natural numbers. Okay, define this one as follows. So I'm going to define it given one order pair S comma T in Sn cross Sn. Okay, we define H of S and T to be equal to, you see both of them are codes of 0, 1, 0, 1, 0, 1. Okay, so when you compare them together, there are some places that they are going to be different because you're just using 0, 1, 0, 1, 0, 1. So when you list these codes of 0, 1, 0, 1, there are some places they are going to be different because otherwise they are all the same. So we count those number of the places and we call it the value of the function. So this is the number of positions, in which S and T have different value. Okay, different values. So that's the definition of your function. Okay, both codes would be given to you, so you just count the number of the position that are going different. So that would be the result of your function. Okay, so this is the function. I give you a pair of codes. You drop it into the Hamming function. The Hamming function will give it a result, H of S and T, which is going to be a number. Okay, so we wanted to try it for us. Suppose n is equal to 5. Means the length of your code is going to be 5. Okay, of 0, 1, 0, 1. We wanted to find each of the following. Find each of the following. The first one, let's do it as we write it down. H of, Okay, 1, 1, 1, 1, 1. Remember the length is 5. 0, 0, 0, 0, 0. Okay, what is this? You see the input must be an order pair. It's an order pair of codes. The codes are the length of 5. Okay, this is 2 codes. So what's the result of the function? The number of the positions in which S and T have different values. You have 5 positions for each code. So in how many positions these 2 codes are different?
5.
5. In 5 positions they are different. So the solution is going to be simply H of 1, 1, 1, 1, 1, 0, 0, 0 is equal to 5. Okay, any question? I just wanted to get your understanding in case, just the position of what is in the domain, what is in the range. Okay, give me another one. What is the value of this one? H of 1, 1, 0, 0, 0, and the 0, 0, 0, 0, 0.
2.
It's going to be 2, very good. You see the positions that they are different are going to be here. This is 1. You see in these 2 positions are different. Everyone else, they are the same. So, you have it in your book. Just want to make sure you know it. That's going to be 2. Okay, any question? So I write a couple of them, just answer it over here so that we have this collection. And then we finish it. And number 3, this is the one that I have, H of 0, 0, 1, 0, 1, and the 0, 1, 1, 1, 0. What is this one? Number of the positions that are different.
3.
That's going to be 3, yes. We can drop the number of the position that they are the same, the leftover to get the leftover. You see the position that they are the same is 1. These 2 are going to be the same. And which one is it? One more. So this is going to be different here. Okay. This 1 and 1 are going to be the same thing. The right hand, 1, 1, 1, 1, 0, 1 is equal to the 3. 3 positions are going to be different to get these numbers. Okay, so make sure I get it right. 1, 2, 0, 1, and it's going to be 0. Yes, these ones are the same. It's going to be 1, 1, 0. It's going to be 3. Okay, so this is the type of function they're going to have. Just for a change to see that how we're going to use this type of ideas in your field. So it's not the case that you don't need it to get this, to know this. Okay, that's it. That's all we need from this chapter 6. Okay, the other part is just operation with the sets. It's not part of your program. So what I do, we quickly get to the chapter 8. Quite interesting chapter. We get back to the definition of a relation on the sets. And then it's not going to be like the one that we did, application to the functions. You see, we defined the relation from one set to the other previously. Now we're going to consider a relation that's defined on a set into itself from A to A. We call it a relation on A. So there are some interesting property over there that you can use in your fields. And we quickly cover 2 or 3 sections. We may cover all of them quickly. Let's see if we can. We have a class on Wednesday, yes. Wednesday, a little bit to the Monday, then we finish it. Because we want to get to all of them, most of them before the Thanksgiving. You see, that's the target. Okay, that's it for today. Any question? So this is a brief section. Just review it quickly. Just 2, 3 questions would be given to you, and mostly people are very happy They just sometimes use the wrong notation because we have the order pair and we have a set. When you write it down, make sure you get it right. Otherwise, we are fine with this one. Okay, have a good one. I have to go. And see you on, on Wednesday. Take care. Bye-bye.
See you Wednesday.